So let's get started. Today we are going to talk about equilibrium of a particle. You do remember in the first lecture we talked about the particle. Say that we idealize things in static in order to simplify the problems. And one of that idealization is the particle. We said that the particle is something that has a mass, but it does not have a size. So when we are dealing with a particle, we are going to ignore the size of the particle. We only are going to consider the mass. So today we are going to talk about the equilibrium of a particle, and especially we are going to talk about condition for the equilibrium of a particle. We are going to say that when we are going to say that the particle is in equilibrium or not, and also we are going to learn how to draw the free body diagram. And it's important matter to learn the equilibrium of a particle, because like you can see here we have a crane, and that crane is lifting a load, and like you can see we have a cord here or straps in order to hold the load. And many times we need to know whether the straps here is going to hold or fail. So it's very important to understand the equilibrium of a particle in order to decide whether the straps here is going to fail or not. Of course, if the strap is going to fail, a disaster will take place. So when we say that the particle is in equilibrium, you say that I have a particle. That particle is in equilibrium. If I said that, it means the particle it's at rest, or it's moving with constant velocity. And moving with constant velocity like the move of the Earth around its orbit. And here, of course, we are not studying the moving of the Earth around its orbit. So here in this course, mainly when we say that a particle is in equilibrium, that means the particle is at rest. It's not moving at all. So if the particle is in equilibrium, it means that I'm going to use the Newton first law. So we have equilibrium, that means the particle is at rest. And if it's at rest, that means I can apply Newton's first law. So the Newton's first law of motion says that if the particle is in equilibrium, then the resultant force, which means that summation of the forces acting on that particle is going to equal 0. So if the particle is in equilibrium, it means that the summation of the forces or the resultant forces acting on that particle is going to equal 0. And in order to understand it a little bit more, we have the Newton second law of motion. So if you have a body or a particle which is moving, it means that the force acting on that particle is going to equal its mass multiplied by its acceleration. And if I have, of course, more than one force, we are going to say that summation of the forces equal the mass multiplied by the acceleration. And from the first law, if the summation of the forces equals 0, which means that the particle is at rest, that means either the mass to be 0 or the acceleration to be 0. And we know that the mass cannot be 0. And that leads us to say that the acceleration is 0. And therefore, that means the particles really move with constant velocity or remain at rest. And like I said here in that course, all the particles is going to remain at rest. That is why it's static. Nothing is moving. And in order to apply the equilibrium equation, which is summation of the forces equals 0, we need to know all the known and unknown forces. So we need to know all the known and unknown forces, and we need to put it in the equation in order to successfully solve the problem. So the summation of the forces here, you need to include whether you know that forces, the value of that forces or not. All of them should be included in that equation. And in order to apply the equilibrium equation, this equation here, to deal with the great ease, you need to draw something called the free body diagram. So in order to deal with that equation here, I need to draw the free body diagram. I think you are familiar with the free body diagram from physics. So what is the free body diagram? It's drawing that show us the particle. We are going to see the particle with all forces that act on it. So a free body diagram, we are going to draw the particle in question, and then all the forces, whether it's known or unknown, is going to be in the diagram. So how I'm going to draw the free body diagram? We have 3 steps need to be done. First, we need to draw the outline shape. Then we need to show all the forces, whether it's known or unknown, with their magnitude and direction. And we don't need to forget that we need to label each force. So we need to put a letter in order to know the force. And for example, if we are dealing with a crane which is holding a load here, if we want to draw the free body diagram for the A particle, for the ring here, then I'm going to draw the particles here, and I'm going to see the forces that acting on that particles. So here we have force pulling the ring from here. I'm going to give it the letter W, and I have the cable A, B, and AC. This one tried to pull the ring in that direction, particle A in that direction, and we have the force here from A to C pulling the particle from that direction. So in order to draw the free body diagram, I need to know, I need to draw outline shape. This one is the outline shape. Then I need to show all the known and unknown forces. And then I need to label the forces. I need to give it a letter to know what you are dealing with. So also, suppose you have a ball like this one here, and you have a force acting on that ball. I need to know how I'm going to draw the free body diagram. For a case like that, first I need to isolate the ball from all the surrounding. So here I need to get the ball and draw it without the surrounding. Then I need to put only the known and unknown forces. This is the known force because I know the value here. Then I need, if I isolate this, that means I'm going to have the weight of the ball is going to act down. And if I have the surface is going to give us reaction. So I'm going to have W here, it could be known or unknown, and I have the reaction. And of course the action is going to be unknown. Maybe you need to know the reaction so that the surface here is going to hold the ball. Sometimes if you have a floor here and the floor is very thin and it's maybe made from weak material, maybe it doesn't have enough reaction in order to hold that sphere here or that ball. So that is why it's important to know the reaction from the floor. The material here should have enough strength and enough force in order to have reaction to support the ball. So here is the free body diagram. So we need to isolate the particles. We need to understand all the acting forces, whether you know it or not. And also we have connections. We have many connections here in order to connect the spring, in order to connect the particles. The particle could be connected through springs or could be connected through cables and pulleys. So let's start with the springs. I know that in physics you have many lab experiments, and one of them in order to calculate the spring constant. So you have a spring and you are going to apply a force. Of course, if you have a spring and if you apply a force, the length of that spring will change in the direction proportional to the force. So if the force in that direction, that means the length is going to increase in that direction. If the force is in that direction, that means the length is going to decrease in that direction. So the length of the spring will change in direction proportional to the force acting on it. And we need to know that the spring should be linear elastic spring. And if you made the experiment, since the force is proportional to the change in the length, that means I have a constant depends on the type of the spring. And you need any material, it has their own spring constant. In order to find that, you need to conduct experiment to find out the value of the spring. Here in the problems, the value of the spring is going to be given for you. And S here represents the change in the length. So before I apply the force, the spring was here. So this one L not here is the initial length. After I apply a force in that direction, what will happen to the spring? The length, it will be increased. So I'm going to have L or L final. The change in the length is going to be called S. S equals L final minus L initial. And that represents the change in the length itself. The S, it could be positive or it could be negative. It depends on the whether you are pulling, whether you are pulling the spring or whether you are pushing the spring. The spring initially was here. If you pull this spring, the value of S is going to be positive. If you push the spring, that means here is the initial. Then you are going to the spring is going to shrink to that point here, and the S is going to be negative because the final length minus the initial length is going to give you minus answer. So if S is positive, then the F pulls the spring, while if S is negative, then the F pushes on the spring. Also, we have the cables and the pulleys. This one is the cables, and this one is the pulleys. We use the pulleys in order to transfer the load from one direction to another. And we need to ignore the weight of the cables. So the weight of the cables here is going to be ignored because the weight is very small. So in order to make the problem, or in order to simplify the problem, we are going to neglect the weight of the cables. And also we're going to assume that the cables here is not going to be stretched. All of this to simplify the problem. And also we know that the cables can support only tension or pulling force. So this one only supports tension. You can just pull it. You cannot push a cable. Okay, it cannot take any pushes. It can only be pulled. And this force always acts in the direction of the cable. So in the direction of the cable here, we are going to have the tension. And also we are going to assume that if this one is the pulleys here, we are going to transfer a load like that. We are going to assume that we don't have any friction. Okay, so we are going to assume that the pulleys is frictionless and the cable is frictionless. We are going to say that we don't have any friction here, because if you are going to have friction here, that will complicate the problem. We need to simplify the problem here. So if you have pulleys, and let's say you have a weight here, and we need to lift a box. So I'm going to use the pulleys here, and I pull this one from there, and the force here, it should be the same as the force there, regardless of the angle here. The angle, if it's what, 30 or 60, it's not going to change the value between T1 and T2. So if I have pulleys, then T sub A is going to equal T sub 2. It's a very important concept. Sometimes we put tricks like that, and the student maybe is going to misunderstood the problem. Here we have example. We have a ball or sphere. It has a mass of 6 kilogram, and it's supported like that. We have pulleys here. We have a knot here, and we have a spring there. And it's required to draw the free body diagram For first, we need to draw the free body diagram for the sphere, and then for the cord CE, this cord for this cable, and then for the knot at C. So it's required to draw the free body diagram for that part here, and that part, and that part. Uh, First, we are going to start with this sphere. In order to do that, I need to separate this one alone. So now I need to calculate, I need to draw the free body diagram for the sphere here. So I will separate this one alone. I will put it here. If I separate this one, that means the ball will try to go down because of its weight. So I have a force which is acting down. And it's not going down because it's connected with that cable here. So the cable will try to push the sphere up. So I have the force from CE up, and I have the weight of the sphere down. So if I draw the free body diagram for the sphere, I'm going to have the weight or the gravity acting on the sphere, and I'm going to have the force CE here from the cord. What if I want to draw the free body diagram for the cord CE? If I have the cord CE, then I have a weight down here, and I have a force from the knot. So if I draw the free body diagram for the cable CE, this part here, I'm going to have the force EC from the knot here. I'm going to have a force EC here from the sphere which is acting down. Finally, I need to draw the free body diagram for the knot here. So if I put the knot here and separate it from all the surrounding, I'm going to have a force FCE here from the cord CE. I'm going to have a force CD from the spring here. I have force CE acting on the knot. And also I'm going to have a force CB from the cable CB here. So if I draw the free body diagram for the knot at C, I'm going to have 3 forces. If I draw the free body diagram for the cord CE, I'm going to have 2 forces. If I draw the free body diagram for the sphere, I'm going also to have 2 forces. And in order to apply the equilibrium in 2D, then here we have the summation of the forces as vectors should equal 0. It's mean that if that's the case, the summation, we learned that how to resolve the forces into x and into y direction. And if you have many forces acting on a particle, first I need to decompose them into x and into y, like we learned previously. Then we are going to say that the summation of the forces in x should equal 0 because the particle is in equilibrium. And also the summation of the forces in y direction should equal 0 because the particle is in equilibrium. And we are going to use that equation in order to solve problems like that. Usually we need to know the tension in the cables so that we need to know whether the cable is going to sustain the load or not. And of course, we are going to use the composition of the forces. We need to decompose the force in direction. I need to draw the free body diagram. I need to apply the summation of the forces in x should equal 0, and I need to apply the forces in y direction should equal 0. So I'm going to use what I have learned in the previous lectures with small tricks, new tricks, and I will be able to know the forces on the forces that acting on the cables. And if I have 3D equation, in that case, instead of 2 equations, I'm going to have 3 equations. Remember, this is the vectors. I have vectors acting on a particle, and that particle is in equilibrium. The summation of that vector forces should equal 0. And we know that we need to decompose the forces into x, y, and z. This one also into x and y and z, and F3 into x, y, and z. And we are going to say that the forces in x should equal 0, the forces in y should equal 0, and forces in z should equal 0. And using these equations, we'll be able to calculate the tension in the cables. So here we have a small quiz for you. Yeah, I finished from the theory. If you have any questions, you could ask me, or if you don't have question, I'm going to ask you. So let's start with that quiz here to check that whether you understand the content or not. The first question here, when a particle is in equilibrium, the summation of the forces acting on it, on that particle, is going to equal, first is going to be constant or a positive number, zero, negative number, or an integer. So what is the answer?
C, 0.
Zero,
C.
doctor.
Yes, very good. Then number 2, for a frictionless pulley and cable, so I have a pulley and I have a cable. I have a tension in the cables here and here. I have a tension in T1 and T2, and then they are related. Then the first choice is T1 is more than T2. The second option is T1 is the same as T2, and the third one, T1 is less than T2, and the last option is T1 equals T2 sine theta. So which one is the right answer?
B.
B. Why do
T1
you want that?
equal T2.
Why,
T2.
why number B is the right answer?
Because the force must be equal in the tension 1 and tension 2.
Yes, but why? Anyone can know the answer? Why they are equal?
Because we
Because it
assume
is a
that
star.
no friction.
Yes, good.
Yeah.
Who answered this?
Karam.
Karam, yes, very good, Karam. Because here we ignore friction. If we didn't ignore the friction, that means some part of the friction is going to be lost here. So you need to increase the force here in order to lift something here. Now let's go to other questions. This one may be a little bit difficult. Assuming you know the geometry of the ropes, Okay, so I have geometry for that rope here, for that one, and for that one. In which system above you cannot determine the forces in the cables, and why? So in this system, if I draw the free body diagram, I'm going to have many forces, the same thing here and the same thing here. One of these systems, I will not be able to calculate the unknown forces. I will not be able to calculate the tensions in the cables. So why is that? Because first, the weight is too heavy, or the cables are too thin, or there are more unknowns than equations, or there are a few cables for 1000 Newton weights. So which one we cannot solve? Like I said, it's a little bit difficult. So if you draw the free body diagram here, you have the weight down and you have the tension here and the tension there. If you are going to dissolve them into X and into Y, in X you are going, in Y you are going to have one unknown or two unknown. Here I'm going to have one unknown or two unknown. I'm going to end up with two equations and two unknowns, and it's solvable. The same thing here. I'm going to have, I have two equations, summation of x equals 0 and summation of y equals 0. And here I don't know the tension in that cable, and I don't know the tension of that cable. So I have how many unknowns? Two unknowns. Here I have two unknowns and one known, which is the weight. I already know the weight. And I have two equations. So if I have two unknowns and two equations, I can easily solve the problem. While here, if I draw the free body diagrams, how many unknowns do I'm going to have here? Four unknowns. And how many equations do I have?
Two.
Two equations. So it cannot be solved. So the answer is there are more unknowns than the equation in number C. Now, if I'm going to have that system here, and I need to draw the free body diagram for the particle A, okay? So which one do you think is going to be the right free body diagram? Is it A or B or C or D?
D, doctor?
It's D, but
I think D, doctor. I think D.
Yeah,
Why
D.
not? Why not A? Why not B?
Because the weight of the subject.
Is missing. Why
Yeah.
not C?
C is
The cable. There is another cable
The
missing.
cable here is missing. Why not A?
Two cables missing.
the two cables
are missing. Yes. Okay, it's nice. I'm glad you answered the quizzes. It's mean that you understand the lectures. I'm going to stop here. So